This is a video about gain distribution in tuner chips. These chips typically have at least two, normally three different gain controls. One is for the low noise amplifier nearest the antenna, another is for the mixer, and the third one is for the IF, which is from DC and up to a megahertz, or in this case up to 10 megahertz. This is an air spy that I'm using for this demonstration. It's a special version of Linrad, where you can see in the upper left corner the gain level for each of the three stages in this tuner. It's an R820 T2 that is used. First, I will show the influence of signal-to-noise ratio by adding attenuation in the antenna. You can see in the S-meter graph that the difference between the peak amplitude and the RMS amplitude, that's white and yellow traces on the S-meter graph, that difference is only maybe 4 dB. I add now 10 decibels attenuation, and you can see the yellow goes down by 10 dB, but the white does not go down quite as much, because now there is some noise. It's not obvious in the loudspeaker signal, but if I add 5 more dB, it is pretty noisy, and you can see that the signal, that RMS to peak levels is now about 10 dB. If I add 20 dB of attenuation, it will be only noise, and you see this is the signal, the RMS to peak on pure noise is a little bit more than 10 dB. So I go back here, and when the signal is noisy, the signal-to-noise ratio is very critical. The output varies much faster than the input. I attenuate by 3 dB now. And that's enough to make the signal very difficult to copy. So I go back. I just go down by 1 dB. 2 dB, 3 dB. So I leave the signal at this level, and we know that a 3 dB loss of signal-to-noise ratio is well audible. And now reduce the gain in the different stages one by one. I start with the LNA gain. 14 is the maximum. If I set the value 15, the gain drops. There is something in the documentation that tells it shouldn't be like that, but that's how it is. So I reduce the gain. And at this point we have lost too much signal-to-noise ratio. So increase gain again here, and instead reduce the mixer gain. And this is the point where we lose signal-to-noise ratio. Note that the signal level now is lower than it was when we started to lose sound quality on the output. So I go up again and reduce the VGA, variable gain amplifier. That's the IF gain.
Alltså jag har upplevt det som det värsta jag kan tänka mig. Att mitt barn liksom inte dör.
And it's clear. When we reduce here, it's possible to reduce even more. I will show what this is good for. You see? We can go all the way down here. The level here, it shows minus 64 or so. The level when reducing LNA gain was minus 35. So that's about 30 dB lower. Means we can tolerate about 30 dB more interference within the passband. But if the interference is caused by a signal outside the passband, the situation is different. And that's what this video is about. The optimum noise figure is of course obtained when the gain is maximum on all the stages. But that is also associated with the poorest dynamic range. If there is an interference that is too strong, the strategy to attenuate, to accommodate for it, is different depending on whether the interference is within the passband or outside. So if the interference is outside the passband, I add some. You can see on 90.6 or so. Here, things start to go wrong. At this point, if I reduce the VGA gain, which is here, this is the point where the desired signal starts to be weak. And I switch off the interference. And you can see it made no improvement. The reason is that saturation happens before the filter. So reducing the gain after the filter does not give any advantage. So it's better to leave the VGA gain high to make the lowest possible noise figure after the mixer. Maybe not maximum, but high, let's say like that. I can instead reduce the LNA gain. And you saw the level went up a little bit before it starts to go down. Here I have lost sensitivity, but the interference is at minus 42. That's when I got problem when only reducing VGA. I can go up now and get compression at this level. It is minus 33. That is 9 dB better. And I can remove the interference for a while. Instead of reducing the LNA, go back with the LNA gain and reduce the mix again instead. Something like this. put back the interference, and I can increase the interference again, but not much, because even if the mixer gain is reduced and the LNA gain is increased, the level into the mixer is the same, or maybe into the mixer output after the mixer gain. So that's where the limitation is for a signal 2 megahertz away from the passband edge or so. If I now move the signal into the passband, first reduce the level to something that is reasonable. The gain is now reduced in a way that is optimum for a signal outside the passband, but that's not optimum within the passband. I can reduce the VGA gain and increase the mixer gain. And I can reduce, that was maybe too much, let's say. We can still hear the signal pretty well here, and I can increase the interferer. When the interference is within the passband, I want the noise floor within the passband as low as possible, while still keeping a reasonable noise figure. So that is a different set of gain settings as compared to the situation when the interference is outside the passband. That's why there are two gain modes in Linrad. You have sensitivity mode for interference within the passband and linearity mode when the interference is outside the passband. And that's implemented in the AirSpy, and for the RTL SDR with the E4000 dongle, maybe later with other dongles as well.